Good morning everybody. We will now try to work out the unsteady solution for the unsteady Bergstrumann problem. It's right here. So when we try to split Z as Z0 plus Z1, and so when you linearize you have the term u dz by dx, so that will have a ux comma 0 dz1 by dx plus there is a ux comma 1 dz0 by dx. Okay, so those are both first order terms, and then you have the diffusion terms here. So this is imposed. So we will say u is u hat e power minus I omega t following the convention of Leuven. So we are following the analysis of from this textbook Unsteady Combustor Physics of T. Leuven, and that is what we are following. And this term we know because we have now derived a solution for Z0, so we can actually find a solution for expression for dz0 by dx. So this part is kind of known, and then so you can bring these terms to this side and bring it there, so that you can think of that as like a forcing or something like that. So and if you use u hat is e power minus I omega t, when you differentiate e power minus I omega t you get I omega times z hat. Okay, so this term would be minus I omega z hat will be like the Fourier transform plus u x comma 0 dou z1 hat by dou x. I will bring these terms here for convenience. Equal to minus u x comma 1 hat. So this is what we need to solve. So we assume we can assume the solution to be of certain form, and then we can try to derive what the solution is. So the solution will have two parts. There will be a particular integral and a homogeneous integral. So we will have to solve for that. So we will first solve for the particular solution, and then we will solve for the homogeneous solution. That is a standard technique in differential equation. So we can, there are several methods in which we can obtain. So you can make a clever guess and say that Z1 hat okay. It makes sense because this is the form of Z0 that we got. So we are trying to this is the form what you get here. So it is like a guess, and then we will substitute this into this equation, and then if we can find the coefficients b and prime, we put prime to make clear that this is the unsteady part. Earlier we used the same bn for the steady part. So we solve for the Bn prime and then we will have to find the homogeneous solution. So that is the method. I hope it is clear. Yeah, Harshini, something bothers you? Okay, this is straightforward. Right? So if you do this and you substitute this in here, you will get the following. So when you differentiate this term with x, you will get a beta out. If you are differentiating y, you do not get that. So when you differentiate with x, that is so wherever this x terms are there, this and this, you will have this beta coming. You differentiate twice, you get beta squared. And when we differentiate with y, this is actually y star. So you have to put this term 1 over W2 squared actually, and when we differentiate with x star, so x star is x divided by this, so that extra term comes. I hope that is clear. So it is just straightforward algebra. So now we just need to multiply this expression by clear W2 by Ux naught. That will simplify things. That is this term we just take out. So you will get omega is 2 pi f Pe W2 over Ux naught plus beta minus d over Ux naught Pe W2 into n pi So all I have done is to multiply this expression by this, and now this will actually dramatically simplify things. So if you club this term, what is this? Strouhal number, yeah, exactly. Okay, so next term is just beta minus we just take one of these W2. So we can write this as W2, W2, and this will cross with this. And what is this? 1 by Peclet number. 1 by Peclet number cancels with Peclet number, so that is 1. We have the beta minus squared, and let us again club terms. So if we take d over, so we cancel one of these W2s, and then we have this. What is this? One over Peclet number. So Peclet number cancelled with Peclet number, there is a 1 over Pe squared left. Ux1 over Ux0, we call that epsilon. That is the ratio of the amplitude of the fluctuating flow to the base flow or the mean flow. So we can just cross multiply and get Bn prime equal to minus 2 over n pi sine n pi W2 over W1 into epsilon beta minus whole divided by minus I 2 pi STW Pe plus beta minus plus pi W2 W1 square minus beta minus squared divided by Pe squared. So this is the expression for beta for Bn's. Hope it is clear. I will pause for a minute so that you guys can. Actually, I multiplied throughout by P W2 by Ux0. So that removed that term. Okay. Oh, so here I should have, yeah. So this now it's okay. Okay. So there is a mistake here. Now it's fixed. Thank you. So now we solve the homogeneous solution. Solve for the homogeneous solution. So we remove the terms from the right hand side. We just solve for the all the Z1 hat terms. So what we have is So we have to remember that y star is y over W2, that is why when we differentiate twice we get this term, and x star is xd over ux naught W2 square. So what I will do is to multiply by W2 squared over d, okay, just to simplify things. So I will get minus I 2 pi f z1 hat squared over d plus u x comma 0 over d So this term cleans up because I have taken this coefficients cross multiplied by that. Okay, now looks like a mess, but a lot of things will cancel. So what is this? This is Peclet number. And d by, oh no, there was a W2 squared. So this is also Peclet number. This is 1 over Peclet number. So they will go, and so let's write this. So I am multiplying and dividing by u naught. So this is Strouhal number and this is Peclet number. So that has come out neatly, plus the mess cleared up because you have 1 over Peclet number multiplying Peclet number equal to dou squared z1 hat dou y star square plus, now the last term. So this goes out. So if I take the 2 out, so now I have 1 over Peclet square, right. So just clean this up and I can say it as minus I minus 2 pi I S T W P E z1 hat plus dou z1 hat over dou x star equal to So we have got a neat equation. We need to solve this, and how would you solve this? Again, yeah, variables separate. So if you club all the x star terms to one side, you would get this equation. So what we can do is to solve it by separation of variables. So we say z1 hat equal to f of y star g of x star. Substitute in here, you will get, I think by now you must be experts in this. Yeah, come on, help me. F of y star into d squared g of x star divided by dx star squared plus f of y star dg of x star divided by dx star minus 2 pi I stw p f g equal to g of x star. Here also I should have the arguments. So f of y star g of x star d squared f by dy star squared. So if you now divide throughout by fg, then you can simplify. So you will get minus 1 over p squared 1 over g of x star d squared g of x star over dx star squared plus 1 over g of x star dg of x star over dx star minus 2 pi p sti equal to 1 over f of y star d squared f over dy star squared. And now we have a function of x equal to function of y, so they must be equal to a constant minus kn squared. Minus is just for convenience, you can do this without the minus also, there should not be any problem. So we have two differential equations, one is of this form d squared f by dy squared plus kn squared f equal to 0, and that would give sine and cos, and then the other one would give e power some beta x or something like that. So let us work it out. This is the solution for f, and g of x star would be of the form C1 exp beta homogeneous x star plus one second, I don't know which one I chose, plus and minus. Beta will have two roots, so one will be positive, one would be negative. So if you substitute this equation in here, what you will get is So if you we can write it nicely as a quadratic equation. So this is a quadratic equation, you can find its roots straightforward. So now we apply the, okay, I will pause for a minute. So we will now apply the boundary conditions. We have a symmetry condition about y equal to 0, so we will apply that first. This will give C3 equal to 0. Cos is a symmetric function, sine is not, so we wipe out, or you can calculate the derivative, put it 0, you will get the same thing. So your f would be C4 cos kn y star. Now we know that dz hat by dy equal to 0 at the wall at x comma y equal to. So this would give, if you differentiate this you will get sine, so sine kn w1 over w2 equal to 0, and when is sine 0? For n pi. So kn w1 by w2 equal to n pi, which gives kn equal to n pi w2 by w1. So this is from the wall boundary condition, just right here. We have to make sure that the solution remains bounded when x tends to infinity, so we have to remove this function, yeah, C1 is 0. Okay, so we are done with the problem. Now all we need is to find the coefficients that we can get from the boundary condition at the inlet plane. So since the mixture fractions are fixed, we said that at the fuel slot Z is 1, at the air slot or the oxidizer slot it is 0. So there is no fluctuation there. So Z1 particular plus Z1 hat. So this would give, or dn prime equal to, I mean dn would be this coefficient C2 times C4, okay, for each of the eigenvalues. So that is why subscript n, because we are summing over all eigenvalues. So therefore we can write Z1 as So this is the final solution. So we know the value of Bn, we had calculated it just a while back. So if you write that, we will get summing over all eigenvalues So this much is the Bn times cos n pi y over W2 times, it's going to spill over but the formula is long, times e power minus omega t. So this is a long formula, but this is the this Pn primes times our function f, which is cos n pi y over W2 times we have the two solutions. So we have the particular solution and the homogeneous solution, and this is the periodic part. So this is a solution. Okay. Now just one last thing, I want to see what happens at the limit of Peclet number being large. That is quite simple. Minus 1 plus 2 kn squared by p squared, actually this should be p power 4, right, yeah. So as Peclet number is large, this term will drop and this first term will dominate. Okay. So that is the solution we had written in the 2 classes back. So you can take a breather, the derivation is over, now we just have to see what it means. We have written the solution with the Peclet number being large, that is when we have this as the argument. So we can simplify that and write it very nicely. You can redo the Strouhal number, write it in terms of LF by multiplying top and bottom by LF, and then you can write a Strouhal number in terms of the flame length. Many people prefer to do that because flame length is something which we can measure very easily, and when a flame is oscillating you can see the flame length oscillating and so on and so forth. And the big mess in the beginning, if you write, most of those terms can be clubbed into dz0 by dx, okay, because there is coming from that particular integral which is coming from this term being on the right side forcing the equation. So to find the flame sheet, how do we look for the flame sheet or the flame surface, whatever? We look for the stoichiometric surface, and that is where we have the flame. So Z is Z0 plus Z1, that is the instantaneous value. So Z is Z hat times e power minus I omega t, but you have to take the value at that particular instant. That is stoichiometric. So this can be recast as so psi naught is the flame position of the steady flame, and then you perturb it, that is psi 1 plus so we will have to implicitly solve for this equation. I will show you how the solution looks like. We will see the look, we will see the results from Leuven. I am showing this with his permission. Where do you see full screen? Huh? No, that was disaster. Now zoom. Okay. So here we have snapshots of 4 instantaneous positions of a forced non-premixed flame, results produced from Leuven with permission. It is forcing at 2 different forcing frequencies, and the one on the left corresponds to ST Strouhal number corresponding to flame length as 0.2. The one on the right, the figure on the right, is for a high frequency Strouhal number of 1.5. So in the low frequency limit the flame just goes back and forth, whereas in the higher frequencies you actually see the flame starting to have wrinkles. So at the low frequency oscillations the diffusion flame just goes up and down gently, but for the other one you see a more fancy wrinkle pattern. So this is what you can calculate by calculating the flame position. Okay, hope this is clear. So to do that we can say so we Taylor expand this. So psi we are measuring the flame position as a normal from the steady flame. That is actually quite convenient because otherwise the flame angle will change dramatically towards the flame tip, and this is same as this. So you can cancel because this comes from the steady equation also, and this term is non-linear, so we can drop that. So this is the, this equal to 0 is the equation, so you will get so combining this we can write the formula for psi 1 comma n as follows. Now this term we can write in terms of flame angle. So when you talk about flame angle as opposed to the premixed flame where flame angle was constant, we had like a tent flame or a conical flame, here as you saw the flame angle was a function of x. So using this we can substitute in here and we will get the final expression which we want. So this is the corresponds to the flame oscillation. Okay. Now let us write the corresponding formula for premixed flame and see whether there is anything in common. So this is for non-premixed and let us write for premixed. So you see the formula is very similar. Now the flame angle is constant if you have, as long as you have a uniform velocity profile and yeah, I mean unless you have convective sorry. Now if theta has to vary, either the flow speed has to vary with space or the flame speed has to vary with phase. So if those things are not happening as we had assumed in our earlier derivation, then theta should be a constant. That is why I emphasize theta of x here, whereas this is just theta. So you will find another difference here, it is just the convection, here there is a cos squared theta sitting here times ext minus I 2 pi ft. So you can see the similarities, this term is same this term is same except for the denominator is different and this is also same. So we should okay, I will pause for a minute, you can look at the formula. So the diffusion flame or non-premixed flame does not propagate. So you have the speed as the convection speed itself. So wrinkles will propagate will be propagating only with this convection speed, whereas that is for the non-premixed flame. For the premixed flame, the flame is trying to propagate and then the flow is trying to come in. So you won't get exactly ux0, but something that depends on ux0 and the flame angle, because flame angle depends on will decide or will be reflecting the flame speed. So that is why you have this difference. So in both cases you have local minima and maxima created through this term here and here, but the difference is because of the nature of the propagation of the wrinkles. In premixed flame the flame itself is propagating, whereas diffusion flame just stands. Okay. Now due to the interference between the wrinkles generated at x equal to 0 boundary and the disturbance locally, you will have this pattern, and that is being reflected in this term, spatial pattern. And so you have this term 1 minus exp I 2 pi f x over ux0, right. This would be nothing but 2 sine pi fx over ux0 times e power I into pi fx over u pi by 2. So this is the sinusoidal pattern and that is propagating, and this you see the speed here. So we have studied two different physical phenomena, one is with premixed flame and one is with diffusion flame, and we are able to see the commonalities, that is both can have wrinkles and both can move, but here the wrinkles move with the convection speed, whereas in premixed flame there is of course a balance between the flame propagation and the flow. Yeah, I think that is it. So we will that thing slept. Can you? Ah, it's coming. Okay, so if you look at the axial dependence of the magnitude and the phase of what we calculated here, on the left half is the amplitude. This is again reproduced with permission from Tim Lewin from his book on combustion dynamics. You see these are the maxima and the minima, and that you can see from this term, and across every wrinkle the flame, or if one part is going up the other part must be going down, right, across each minima. If you have something like this, here it is going up, here the flame is coming down. So that is why there is a shift of 180 degree at each of the nodes. So I will wrap up this lecture here, and since we have studied diffusion flame and found how it behaves in an unsteady way, of course you can calculate the heat release rate and so on from this, get a global transfer function and so on, but what is really interesting is it has a lot of similarities with the premixed flame, but there are some differences also. First of all, in the analysis the main difference was that G, it really has meaning only at the flame, whereas Z we have to solve for the whole field. So we actually solve for the whole field, and from there we actually look for the stoichiometric surface, and then we calculated how the flame is responding, and then we got the flame response, and the flame response also behaves in a very similar way with the premixed flame, that is you have a spatial pattern which is moving, but the difference is that in here it is only the convection, because the flame itself is not propagating, whereas premixed flame is propagating, so that shows some difference. So you can see in these two expressions the commonalities and the difference. So this is a good exercise to help you to solve things mathematically. Of course this is a simple problem, even you can try more complicated things, everything may not be analytically tractable, but then you can actually solve things numerically, but this will be like a simple benchmark problem. Okay, so in the first half of the class we studied acoustics, wave propagation and so on. In the second half we studied thermoacoustic instabilities and we looked at a variety of different situations. We analyzed the problem in harmonic domain and also in the time domain, and we looked at the model analysis, non-model stability analysis and so on. The key to all the analysis was, one is the stability part, where you either solve the equation in time domain or with the or you solve for the growth rates and frequencies, and then we also looked at singular value decomposition, explained how that characterizes energy growth and so on. But central to this calculation is the input to the model, which is the flame response, how the flame behaves in response to the fluctuations, and that we have made models for several different systems. For example, just now we did diffusion flame, earlier we did a premixed flame, we have studied a lean premix pre-vaporized flame. So like that, for each of the situation you can construct a model for the unsteady heat release rate, and then you plug it into the corresponding wave equation, and then you solve in whichever way you are solving. So I hope you will be able to extend all this analysis to your thermoacoustic system and be able to analyze what happens to it, both the linear stability and the nonlinear stability analysis. Thank you.